Thank you very much for the introduction, and thank you for inviting me to be here, to all the organizers. I'm sorry I couldn't be here yesterday yet, but I look forward. It's good I'm directly at the beginning, so there's plenty of time for discussions, I hope. And I'm sorry I still have to plug the power, I just saw. But I can speak meanwhile. So it's a very generic title, Levitated Optomechanics, and the purpose is mainly to show you a little bit about optomechanics and what one can do today there without going very much into depth, and then show you how I think that levitated optomechanics can actually bring something very, very new to this kind of system, and also that we can control this system very well. The reason there's no quantum in the title is because the system is not quantum yet, but will be soon, I hope. So just give me 1 second, I'm sorry. So as you can see, this work is, I will cover quite some topics, and therefore there's quite a big list of people, mainly in Vienna, Aspelmeyer group, my own group, and then also our main collaboration with Eric Lutz and his co-workers. So we'll cover a lot of things there. And I will focus also down a little bit not on all the applications that there is. Maybe something like force sensing that many people think about with levitation is also relevant in the context of this workshop. My main ideas lie in the direction of statistical physics and thermodynamics. And this is also why I start with this slide. So as is no surprise to you, of course, we have a different, when we enter different regimes of parameters, we always find new physics, and it's very interesting how one can add to thermodynamics when looking at very small systems, for example, in biological systems or so, where thermal fluctuations are relevant. And then if one gets even smaller, and usually like not so many years ago, one would probably show here an atom or small NV center or so. But actually nowadays we don't have to be so small to have a quantum system anymore. This is an optomechanical device. As you can see, it's on the order of a few micron, and it's really the mechanical motion in there that goes into a quantum state. So in this kind of man-made systems, we can actually look at quantum fluctuations, and one of the interesting questions is, of course, if we combine this with the notions of thermodynamics, what can we do and what changes? So I will start a little bit with these optomechanical systems just to show you what one can do and very roughly how it works, and then show you how optical levitation brings these two worlds kind of together, and therefore I hope will at some point lead also to a kind of nice experimental platform for quantum thermodynamics. So first part on the optomechanical systems, and this is what is usually shown in the beginning, that there's a whole plethora of different kinds of optomechanical systems. Actually, they can have all kinds of masses and sizes, and it's always described by this paradigmatic Fabry-Perot cavity. So some light would be coming here onto this cavity, and there's a mechanical resonator as one of the mirrors, and when this mirror moves, then the length of the cavity changes, and therefore the wavelength for the standing wave changes. So we have a different resonance frequency, and in a linearized way, because these motions are typically small, we see this d omega over dx as the length change, and this is how the light field actually couples to such a system. So when light comes here, it exerts a radiation pressure on this mirror, but at the same time, of course, the mirror modulates the light field because the cavity resonance changes, and the coupling would be quantified usually in such a way. So if we look at this quantum harmonic oscillator, then we have some ground state of this oscillator with a certain size. which would characterize how much the length changes for in the ground state. And this as the length change times this differential here gives us the coupling. So if I add one phonon, this is roughly how much frequency modulation I get in my system. And it's true for all of these systems. So one could have a toroid where light goes just around in a circle, and then the size of this toroid changes. I will talk a little bit about how dispersive coupling works. That's also what we use in levitated system, where just material in the light field leads to this modulation. Or this is what I showed you before as a SEM picture, where a stretching of some photonic crystal actually changes the cavity. But you always have to just think about this kind of coupling of a length change to the cavity resonance frequency. And if one now would use just a single photon, which is in principle thinkable, in the cavity, then the interaction would be this one, where we just have the photon number operator, because that's how much radiation pressure acts on the mirror, times the position of the mirror. So these two are coupled with this G0, which I just showed you before. But it's still too small. We're trying to get this kind of systems, but it's still too small. So what we usually do is have a strong field, just a laser field, some coherent kind of state that goes onto the cavity. And then things can be linearized, and we can look at the phase, or at the position, or if you want, amplitude quadrature of the cavity, and the x quadrature of the harmonic oscillator. And we have this linearized form of the coupling, where the coupling is enhanced by the strength of the field. And this allows us to actually work with this, even if the coupling is weak. So just to give you some numbers, for example, in a typical of those system, there would be a megahertz oscillation, and the coupling is on the order of a hertz, and so it's very weak. But then if we just have a few microwatt in the cavity, then this is already enough to see some coupling. So here's the coupling we work with, and this sounds almost a bit boring. But then when you look at it closer, so here again the same picture, light field driving the cavity. And now if we go with the light field here in frequency below or above the mechanical resonance frequency, which you see here in a kind of frequency space picture. So here's what the frequency, resonance frequency of the cavity, and now our pumping light field is, which comes in here, is a little bit too little, has a little too little energy. Then we actually need to take energy out of the resonator in order to get excitation in the cavity. Wow. Is this me who is shaking this so much? No.
It's a mechanical oscillator.
Yes. Electronically enhanced. Yes. So this way we can actually create a situation where a created cavity photon annihilates a phonon in the resonator, and vice versa, and this would be a beam splitter type interaction. Or we can go to the higher energy side, and then whenever a photon in the cavity is created, also a phonon on the mechanical oscillator is created, and this gives this kind of entanglement interaction. So we don't know how many of these excitations are done, but they're always the same number in both. So this is a squeezer. And if we are just on resonance, then we have the coupling I wrote down before, and this is essentially reading out the position. So in the end, this is how one typically would measure just the position of the resonator over time, because the light that goes out of the cavity is modulated in phase, and this modulation in phase is something we can measure very, very precisely. And all of these tricks have been done in a set of experiments, which I don't go through in detail, but just some of the major achievements There's more by now. Okay, one thing that people always wanted from the very beginning was to use this type of interaction here, where you can get energy out of the mechanical resonator to cool the system into the ground state. And this has been achieved both optically and with microwave cavities. And then one can play tricks, for example, driving with two sidebands, right? Not only with one, which if one goes through all the math, leads to a squeezed target state. So now the mechanical oscillator would not equilibrate, if you want, anymore into just a coherent state, but it would be squeezed in phase space. Which is something desirable, because if you have a squeezing, then you might have a better position resolution, for example, as they want in gravitational wave detectors or so. So squeezed states of motion really be below the standard quantum limit. Then, as we always talk here of two harmonic oscillators, you would think, well, maybe it's always not so terribly quantum. Squeezing is still something you can get, but how do you get further? How do you get something nonlinear with all these linear systems and interactions? Well, non-Gaussian quantum states of motion can be produced. For example, and this is not really only optomechanically. Here, a microwave circuit is coupled to a superconducting qubit, and one can do kind of Ramsey-type experiments or so, simply because one has here a two-level system that one can play with. But also, in a very similar fashion, for those who know that, in a very similar fashion to down conversion, this process here looks like down conversion, and if you just see that you detect a photon that comes out of the cavity, you know that you created a phonon, and just a single one. So in this kind of experiment here, one essentially does post-selection on the detection of a photon, and then one knows one created a phonon in the cavity, and that was pushed further and further now. By now, one can essentially entangle two mechanical resonators that are far apart with such a detection scheme. And entanglement between the light field and the cavities is also possible by this squeezing interaction. And so this is roughly where we are with the optomechanical system. So I'm saying we can create quite a set of quantum states, and one can have quite a different number of mechanical resonators in the quantum regime. But we are always working with these harmonic systems with very few exceptions. Now, optical levitation was initially thought to be just another way of getting a harmonic oscillator. And the idea was, well, if I take a particle and I put it in a light field and then I evacuate the whole environment, there's nothing it can couple to anymore. There's nothing that dissipates. So I should get super nice quality mechanical resonators, because in the end, what it always boils down to is that you don't want your system to interact with the environment. Which reminds me that I forgot something. I'm sorry about that. So, important figure of merit in the whole thing. I told you there's this interaction, but unfortunately we cannot work forever with just this interaction because the system is open. So there's losses of light from the cavity, of course, which are not so bad because I can detect the light that comes out and I can use this. And there's losses of the mechanics, and this is usually to a thermal environment in whatever kind of system I created here. And if I compare the coupling squared to the losses to the environment, which depend on the temperature and the coupling to the environment, and with the losses from the optical field, then I need the coupling to be essentially stronger. So this value called cooperativity needs to be larger than 1. And this is what one has to achieve for all these kinds of schemes. And the coupling from the environment is the lever that we want to use with the optical levitation. But in the end, it turns out that optical levitation can do much more than just create a harmonic oscillator that is very good. But because this is the beginning of the story, it's also where I will start. So it started actually already in the 70s. So Arthur Ashkin played around with optical trapping. He saw that one can trap particles in liquid, and then he also showed that you can trap particles in air. Actually, he already trapped 10 micrometer sized or 20 micrometer sized droplets in air by having the radiation pressure from a light pointing upwards holding this particle here. And he could go down to a pressure of 10 to the minus 6 millibar, which means that for these low frequencies he had, this thing would oscillate once you kick it for a few days already. The system was not stable enough for this. But this was actually the beginning of a whole lot of experiments on the one side in biology where optical tweezers are used, but also on the other side for optical trapping of atoms and so on, which is of course also levitation just of small objects. And the interest in levitating really more massive things like nanospheres of the order of 100 or so nanometer, 100 nanometer, here it was 70 nanometer. That came only when this idea came up that optomechanics is nice and couldn't we get a nice oscillator with levitation. And I always like to show this graph here because it shows a little bit what levitation can do. So this is a collection of all kinds of mechanical resonators, and it plots the rough volume of the thing versus the quality factor. So in the end, how many oscillations can I get until I have a 1 over E decay of the energy of the system. And all these lie more or less on a line. But then if I look at levitated systems, then this experiment by the Novotny group and Jan Kiesel already showed in the very beginning of this levitation ideas that we can get far above this line with a Q of 10 to the 6 or 7 in the beginning, and by now it's a mechanical quality of 10 to the 8. So that is to say we have a 100 kilohertz oscillator with a Q of 10 to the 8. So once you kick it, it will ring down for an hour or so. And if one kind of extrapolates the Ashkin experiment, it would already be here. Now, there's a little spoiler, which I also want to mention. We will not get much further than this because the pressure, if I go down in pressure, the air goes away and I don't have any interaction with the environment anymore. But what I do have, of course, is light goes onto the particle and is scattered in all directions. The particle is much smaller than the wavelength. This is why it's a dipole emitter. It just goes everywhere. And this is the recoil from the scattering, well known for atoms, where it's much worse, so to say, will heat up the motion of my particle. So there's also damping associated with it because there's also a Doppler shift on this light. And in the end, I will show this a little bit later. In the end, it turns out that you have a new temperature bath. And this, the mechanical quality, is essentially limited to, or the effective mechanical quality, if you want, to 10 to the 8. And effective, I say, because the quality is actually much better, but it's also a much higher temperature that you couple to. And this is the tool that has been used. I'm still talking of optical levitation without any cavity. So what people started to do is have a microscope objective, focus the light down, and then one has an oscillation in a harmonic potential, actually in 3 directions. And then if I want to lose energy in the system, I don't necessarily need a cavity. I can also, whenever it runs uphill, I make the potential very steep, and when it runs downhill, I make it very flat, and this way I always lose energy. So this is parametric feedback cooling. So I do this many times, and then after some time, I have a center of mass motion of the particle that becomes very cold. Now, if we do that, so this has first been done to very low by the Novotny group mainly. And this is data from our lab, actually. So if we do that at, so say 10 to the minus 2 millibar, then we can cool down, we equilibrate at a certain temperature, then we switch off the cooling, and the center of mass motion for all three directions equilibrates to 300 Kelvin, and then I switch it on again, and it goes down again. So this requires a modulation of double the frequency, so on the order of 100 to 300 kilohertz or 400. And from these ring up measurements, we can actually know how much the heating in the system is. And if one plots that against pressure, then you see that with lower and lower pressure, it goes down linearly. We have less and less heating in our system. And at some point, it levels off. And this leveling off is exactly the effect that I've been talking about. Recoil heating heats up the system, and it has been shown by these people who did that also experimentally first, that one can get a very simple equation for the up to some factor for the final temperature of this. So the temperature of the bath goes with the photon energy, simply. And that is not as much as one would expect. It's actually lower than the trap depth. That's 10,000 Kelvin. And our trap depth in this kind of systems is like 50,000 Kelvin or so. And this cooling in this paper goes down to 60 phonons. Meanwhile, to my knowledge, we're at roughly below 20 phonons. Not we, but they are at below 20 phonons. So it's really not that far to go into a regime where we go to the ground state motion. The challenge is that parametric feedback becomes very inefficient and that you need a very, very good position resolution. Now, as I said in the beginning, I think that this is also a very nice system to go towards statistical physics and thermodynamics experiments. And there's by now surprisingly many experiments already on this. This is why I show you these two reviews and just quickly summarize the directions that people have gone to. This is very recent and really has everything inside, I think, that has been done to this point. So apart from the things that I will still show you, one thing people were interested in was fluctuation theorems to look at. I will show you something on this also. Another thing that people studied was, as you will see, a Kramer's turnover experiment, where you essentially want to study the rates at which a particle jumps due to Brownian motion from one well to the other. This is quite some interesting and not so easy physics behind it, and this could be verified experimentally. And also, and this is, when you look at this setup, this setup here, this is actually pretty simple. It's, if you like, it just needs to be done very well. With this setup, you can do almost everything that has been done with these optical tweezers so far. You just need to detect the motion of your particle, do some operations on it, or add something, and then you can study the nonlinearity of the potential far from equilibrium behavior, the fluctuation theorems I mentioned, and one can look at stochastic resonance by driving the system out of stability. So it's really very versatile. This, what I'm going to show you now, is one little workhorse that we work with. It's a bit different than the tweezer approach that I showed you before. So here what you see is a light field that goes into a hollow core fiber from two sides, creating a standing wave. And this standing wave does also trap these particles. And so this is a hollow core fiber. In here is a 10 micrometer big hole, which one can evacuate. This is a SEM picture of our particles. And one can trap them in the light field and then have a conveyor belt by detuning one of the light fields that pushes them into the fiber. So that looks, just for a little bit relaxation, this looks like this. So that's a particle in mild vacuum, and one can very well control the motion in this fiber. One can not only control it, that was the main idea in the beginning. We wanted to have a delivery of particles, but one can also study the system very well. So we have a readout of the motion of the particle in all three directions. And we can study the frequency in there, so that gives us some insight onto how the intensity is distributed. So the single mode fiber is not as nice as one would think in the beginning. And we can pull it out of the fiber, the particle, and then because the light spreads open, the frequency goes down. There's a lot of things one can play around with this system. What I want to show you goes more in the direction of this thermodynamics experiment here. So we added to this, here you see another schematic, we added to this conveyor belt structure, we added another light field that goes in here and is pushing the particle. And as I said, we can also detect the motion in 3D. Here we are only interested in one direction. And then we can apply some feedback. The feedback cooling here is slightly different whenever so it's proportional to the velocity of the particle. So we add this little term here in the Langevin equation by our feedback. And that means that effectively we simulate a bath that is at a different temperature. So what we can do by controlling the gain of this feedback, we can control the effective temperature of this bath. Not changing the noise of the Brownian motion, but changing the damping. So we also change the coupling to the bath if you like. So for those interested in number, we have almost 1 micrometer particle, and we simulate a reservoir by the feedback. And what we want to do with this is study far from equilibrium behavior. What is more known than what we want to do here is the Jarzynski equality, where one can push a system far from equilibrium by some mechanical action. And then, for example, we could in our system have the particle trapped in a harmonic trap, and then we do something to this trap. For example, we make it more stiff, and then the particle can equilibrate again, and these two states have some Helmholtz free energy. And if we want to know the difference in this free energy, we can do that super slowly and just look at how much work this applies to a particle on average. Now the Jarzynski equality tells us it doesn't matter how fast we do this. We can do it as fast as we want. We don't evaluate the average of the work, but this exponential average. And then we can also determine this difference in free energy. And in many cases, this has been done for mechanical driving. What we can do now with this feedback is we can do a temperature driving. So when you switch the temperature of your system very quickly, it also goes out of equilibrium, of course. And so we could, in principle, do any kind of temperature trajectory here. And then this paper by Williams, Searles, and Evans tells us that we can also evaluate for this free energy. Actually, it would be general. One can do mechanical and thermal switches in the most general version. And one part why I show you this is not only because I like that we can do that, it's also because it requires really a fast control of the system. So the change in temperature is taking place over only a few oscillations. So here is one example with 36 microseconds. This is not at the extreme. We have faster and slower protocols. So we linearly change the gain. That gives a hyperbola in the temperature, and the system cools down while we do this. And then we can do this 10,000 times and take all these kind of trajectories and evaluate this quantity here and get this result. So one expects that in this inverse temperature times free energy difference, nothing changes when we do this cooling. And these are simulations and experimental evaluations for all kind of different ways of evaluating this. So just to use the equilibrium approximation, where we do this really slowly, of course gives for very slow protocols the same result as the one for the fluctuation theorem in blue. But when we go faster and faster and faster, then we see that we would get a wrong result for the just normal average, but for the fluctuation theorem, we always stay in the same area. And the white bands here are because of some systematic errors in the experiment that we take into account to see how far the spreading of the result we would expect. So this actually works very nicely, both in the detection and the control of the system. How much time do I have? Okay. Still 10 minutes. Yeah. Thanks. So this is an example for the fast control, and the thing we are currently working on is that a temperature and a mechanical change in the system at the same time. But there's much more still. So this was mainly because we are fast, but what you can see here is what people do in liquids with optical tweezers. So they can do much more than just trapping one particle. Huh? They can play Tetris. And so we have a lot to do still until we did everything one could in principle do in levitated systems. And first little experiments have been done. So for example, well, little is maybe too much to say. It's not so easy to do it in a levitated system because you lose your particle much more easily. But so this was the Kramer's turnover experiment, which I already mentioned, where two lasers were focused and then one looked at the jumps of the particle from here to here. Or in another group, people actually trapped two particles nearby. There's some optical forces building up, and one can measure this attraction. Or we are currently trying to do this as well. And what you can see here, we make such a double well and then switch from double to single well. When it gets bright, it's a single well. And the particle always drops down in one of the two wells in this movie. So it goes back up, and now it drops left or right. This was just to try out if we can somehow do this. Now the nice thing about it is that this switching between this, for example, double well that we have here or a single well, we can also do with a frequency that is higher than the particle frequency. So in principle, we can completely control the spring constant in here if we like, and all of this works with the readout that one has. So as you saw, people in the other lab could cool to something like 15 phonons. That requires a resolution on the order of like 15 ground state extensions. So I think there's quite a lot potential in here. What we are currently doing is we're looking at the experimental realization of a non-equilibrium information erasure protocol that has been on the archive just a few days ago. So what I said was we can control very well this potential in optical levitation, and this takes us quite beyond what we can do with a simple clamped mechanical resonator. Still, we have this nice decoupling from the environment, so we don't have so much dissipation. But somehow we would like to substitute this missing environment for something else. And And this is what the cavity can do. So I showed you the cavity-optomechanics in the very beginning because we can do all the same tricks here now. So this is kind of my dream setup for the next time. This will still take a bit, but in principle, all the tools have been shown. So to summarize this a little bit, we get rid of our environment, and we can create a new environment by some reservoir engineering via cavity-optomechanics, and we can control our potential. And this has sparked many ideas. The first ones were more in the direction of matter-wave interferometry, where one actually drops a particle and then studies how one can get interference fringes here. But of course, we are also looking into this thermodynamics direction. And already the fact that you can cool with the cavity and change the frequency of your potential allows to realize this kind of Stirling type engine. There's not so many people as do optical levitation working with cavities. All these people have shown cooling in cavities, and there's, to my knowledge, not more yet groups that are actually doing this in cavities. Different configurations. So we are trapping the particle inside. Here they are flying through a cavity in this experiment and are cooled in transition because this is meant to be a source for matter-wave interferometry. Here there's also an ion trap involved, so and here they are doing it essentially the same way as we do it now, as you will see later. I speed up a little bit to still show you how that works in the cavity. So in the cavity, when you think about it, the particle, there's a standing wave, and the particle could be somewhere in here. And if the particle, so the cavity frequency, independence of the position of the particle, looks like this. There's some prefactor, and then there's the standing wave. And if the particle is in an intensity maximum, we minimize the frequency of the cavity. I should have made a delta here. So this is the shift in frequency of the cavity. So if we want to minimize the energy in the system, the best the particle can do is go to the intensity maximum, which reflects the trapping potential. This is not where we get our optomechanics. If we push the particle to be here on the slope, then this can be approximated like this, and we get a linear coupling, which is exactly the same coupling as in the cavity-optomechanics I showed you initially. Long story short, we did that in the old days to trap the particle directly by a cavity field, and then by detuning a control field, we could cool it. So this is a noise power spectrum. The width of this reflects the damping in the system, and when we detune our driving laser, then we go to this cooling interaction, and this gets wider, meaning that we add damping to the system. And we had some cooling to 50 Kelvin or so at the time because we were at very high pressures. And then we had some idea on how to do the Stirling engine, which I will skip due to time now. I think you can ask me if you're interested. So one can now change temperature and frequency, and thereby one can realize an engine. Now, how far do we need to go into the quantum regime? So are we still very far from it, or do we have to change much? These are my last 2 or 3 slides. So what we do now is we hold our particle from the side into the cavity, and this is essentially showing it, only the beam is much wider. The particle is in the cavity, and we can hold it all of the time, independent of the cavity field. It turns out to be very convenient. Then we can move it around in here, and if we move around the particle, then we see more or less a modulation of the phase transmitted here, and that gives us this kind of noise power spectra. If they are high, there's a strong coupling. If they are weak, there's a weak coupling, and we can map So when you look, for example, at the blue curve, that's the linear coupling, we can map the field that is inside the cavity here. So one has a very fine resolution of the electric field, or actually the intensity inside the cavity, with a step size of roughly 8 nanometer for this motor driving the microscope objective. So with that, we position the particle at some kind of optimal place, and then we need to know how well we couple to the cavity in a good number. So what we use there is called optomechanically induced transparency. It's very close to EIT in spirit. We go to the red sideband, so we scatter photons into the cavity resonance, and then we modulate this laser such that there's an additional sideband. And for this one, we change the frequency. That's what's running over here. And when they hit each other, the photons from the mechanical resonator and the other one, then they show a destructive interference. And the width of this destructive interference feature here gives us the coupling over the cavity line width. And from this, we can determine the cooperativity. To remind you, we wanted a cooperativity larger than 1 in order to be able to do a quantum experiment. We know the heating from the measurements that I also showed you before, where you saw that the recoil is actually playing a role. And we know this chi square over kappa, the interaction over the cavity line width from this measurement, giving us a cooperativity of 0.1. So that's an improvement of something like 6 orders of magnitude to our old experiment, but not yet there. So we will have to make the cavity mode volume a little bit smaller, but this is not the biggest problem. In principle, it works very well. And 2 days ago, I received a message that we could actually do both this recoil heating measurement and this coupling measurement at the same time at 10 to the minus 5 millibar. So to wrap it up, what I say, I hope you saw that the control we have over this kind of system is very well, and I would be very interested to see some discussions on what kind of ideas people have on if you have this capability of manipulating your potentials very fast. We can also change the environment with the cavity, and the plan is to put all of this together and go into the quantum regime, which will open new questions. On the one side, we know that our engine will become less efficient if we go to getting very cold. On the other side, we know that squeezing might bring us some advantages. So that's to come in the future. This is the team. So blue is on the cavity team, and green is the people on the hollow core fiber, and red are the ones that make the nice double well potentials. And here there's our theory friends. And of course, many thanks go to Markus Aspelmeier, who is, I'm kind of in a superposition of working with him on the cavity experiments and working myself on the complex potentials and so on. So thanks for your attention.